Hello, a very warm welcome from my side. My name is Kostas Chinarakis. As Communication Officer of DGE Rollout, I have the honor to guide you through this event. DGE Rollout is an Interreg project of the European Union. Our vision is to foster deep geothermal energy as a climate-friendly heat source in Northwest Europe, and subsequently nurture the region's economics and well-being of the citizens. To achieve this, we want not only to generate expertise, but also make it available and provide information for stakeholders, investors, and everyone who accompanies the way to geothermal energy. Therefore, I'm very pleased that so many of you joined our webinar today. I'm sure you can take away useful insights. Providing you with the latest geothermal knowledge is the job of today's speaker, Jeroen van der Vaart. He is an expert of geothermal research and especially of geological 3D modeling. For nearly a decade, he worked on geological modeling in the oil and gas industry. Today, he uses this experience to help making geothermal energy more accessible. Right now, he conducts research at Technical University of Darmstadt. On the one hand, creating new publicly available subsurface maps for the Upper Rhine Graben. On the other hand, providing workflows to reduce the uncertainty of such geothermal models. I am very happy that we have him today with us. Jeroen, the floor is yours.
Thank you, Costa, for this wonderful introduction. I almost feel like an expert now. Luckily, we have also many experts here, and for those who are not, well, soon you will be a little bit more informed. So let's kick off this first webinar. Now, my name is Jeroen Vaart from the TU Darmstadt, and together with my colleague Matthijs Vrij, I have created a presentation about resource mapping for deep geothermal energy, and we're going to look at more insights through new 3D modeling of the Northern Upper Rhine Graben. Let's go ahead and jump right in. So my colleague here, Costa, has already introduced you a little bit into what the DGE-ROLLOUT project is, and no, I'm not going to repeat this part where we mentioned what we are trying to do, because what we want to do is create more geothermal energy knowledge. You've seen here our partners, which are here on the left side, and but what we are looking at today is this specific area in the Northern Upper Rhine Graben, which we're going to use as an example for more deep geothermal energy and what we can extract from there. Now, for those who are really new to geothermal energy, a very quick summary. Deep geothermal energy is basically we're going to extract all the heat, or we're going to extract heat from the earth. And we're doing that by extracting the water that's in there. And of course, you can't always extract all the water in there, because at a certain moment there's no water to extract anymore, or at least not enough. So what we do is we inject water from one side, and then we extract it with another well. And as you can see here on this example of this doublet, is that it will go from one side to the other one, to the it will be pumped in, and then once it moves towards the one that is pulling out, because of the pressure that's trying to pull out, it will take the heat along the way that can extract from the source rocks. We can do this directly by primary permeability, but also by stimulation of fractures. There are also these days, there are more and more systems which are actually just working with a closed loop system, which basically would connect in one system the injector and the producer together. Well, once we get this heat up, we can use it either for electricity, if it's warm enough, and then you need to think about that we need water of about 140 degrees. And if it needs to be, and if you have less heat, then you can still use it for heat production, which is a very large part of our energy household in the Europe, especially on days like these, where at the moment here it's about 1 or 2 degrees. So we do need that heat. Now, why am I actually talking now about the Northern Upper Rhine Graben? The Northern Upper Rhine Graben is a bit of an interesting part in Europe because of the older times, it has been extended. And what extension means is that then the crust, it will get thinner. And when it gets thinner, it gets easier the heat from the part that's below it, from the part where the earth is still liquid or somewhat liquid. That heat will come up easier because it's closer to the surface. So that's really, and if it's closer to the surface, we can, that means that the layers in between will also be, the crust in between will also be easier heated towards the surface that we have now. So this area is underlain by the Variscan Basin, which you can see here in blue. In this case, also have some Jurassic sediments incorporated in this because it was a little bit easier for the model. And that is filled with some Cenozoic or tertiary sediments. And well, yeah, that becomes easier that we have this elevated geothermal gradient. And why then also is the Upper Rhine Graben very interesting, and especially Northern Upper Rhine Graben in that series, is that there are a lot of major settlements here that could use electricity or heat. And then we talk about cities like Mannheim, Frankfurt's not too far away. So all this is very useful to have them nearby. Now, here you see such an example of the geothermal gradient where here you see more a standard geothermal gradient in the dotted line. This is an example of the well by Sul-sur-Forêt, which is also the Rheingraben, the Upper Rheingraben, which you can see here. But because of this, you see that, well, there's a large anomaly and the heat is really closer to the surface. Sul-sur-Forêt is a little bit of a very nice case, but in general, you will see this throughout the entire Northern Upper Rhine Graben, where the heat is just close to the surface. As you can see here, already at 1 kilometer, there are already near 120 degrees. So, what are we going to do with this heat? Well, is this just Sul-sur-Forêt? No, it's not just them. You can see here a few other wells, and some wells that are still in operation, or some that might actually not be in operation anymore. Unfortunately, also some failed projects, and soon we'll also dive in how we can reduce that. So as you can see here, it's not just in one place or anything that would be like a pipe dreaming. It's actually being used quite a lot here. So now, to start with a project, you will need to have some idea about what's below the subsurface or what's in the subsurface. And for that, people make a lot of models. And here you see a list of some interesting 3D models that have already been produced. And many of these are actually freely available. You can just Google them online and you can get to them. They're not all for the same purpose. Some of them are for deeper areas, some of them are for less deep areas. You can look at them in different ways. But these 3D models are very important because they give you a very good starting point of, okay, where would an interesting spot be? Not just because, yeah, if the heat at a certain location is actually quite deep, or if the area is just not suited for it on the surface, then you can't do anything with deep geothermal energy anyway, because you can't, yeah, it's too far away, for instance, or it's too expensive or too risky. Now, there are quite a few models, and which, as I mentioned, they are freely available, and particularly noteworthy of these models at the moment are the Georg model and the Hessen 3D models, which have a very clear and are quite easy to access on are very clear and are quite easy to access on their on their data. So now, why are we then still making another model in DGE-ROLLOUT? Well, what we are doing is refining the model, is refining a few models or the existing models, and we're adding more details to it, and we're also applying uncertainty modeling and quantitative techno-economical resource assessment. So in other words, we're giving more than just giving you a subsurface, where the goal is to actually give you a more in the leg up that you could use for your starting a project. Now, how we do it is we're doing this with inputs from the models, and we have not just we're building upon the shoulders of the giants before us as well. So what have we started with? Well, we are starting here, as you can see, with a model, and this model has been created by well logs, as you can see here. And we have core measurements in there. After that, we have a temperature model, which we gotten which has been modeled for the entire Germany, which the source you can see here. After that, we using the interpretation that has already been done on the previous projects that I mentioned, the Hessen 3D process and the Georg models. But not just them, also we also got some extra new lines that we have been working on, renewed interpretation, which has been done earlier, which you can see here is a nice seismic interpretation done, which should be published early next year, depending on how quick the processing goes. So all this data is available, and we use that to create the model. Now, I can talk long and short about how this all works, but in the end, we want to know how much heat is available and how much heat can we extract. Now, to see how much heat is available, there's actually quite a simple formula, which is the heat in place formula, which is, and I go along with it as I've been modeling it here, the volume. So you can see here 3 layers that we have here, which are the Pechelbrom, Vaart, and the Niederrode Formation, which are all part in the stratigraphy in the Northern Upper Rhine Graben. This volume is just how much rock volume is available in a certain area. Then the density, how heavy is the rock? Then the heat capacity, which means how much heat can a rock hold per Kelvin or per degree Celsius, which means that to raise it, there needs to be certain energy put into it to make a rock warmer. And to extract it, you have to can take the same heat out, the same energy out, which means the higher the heat capacity, the more heat you could extract from a certain volume of rock. And then there is, of course, important the temperature difference, because we want to lower the moment we extract heat from a rock, that means also that the temperature goes down, and that's very important to have here. In this case, the model that you see here, we have what we're using here is we're comparing it with surface temperature, which on average would be 11 degrees, a lot lower than you would expect, but that's more or less what it is, 11, 12 degrees. And this is useful for further calculations, which you could do on different levels. In this case, we chose for 11 degrees. Other alternatives that you could use is how much heat do you actually want to extract, which would be, for instance, until 80 degrees. So then the temperature difference would, of course, be lower. And all of this combined, we create something called heat in place. Now, and the heat in place here, you see here on this grid is quite a lot, because there's a lot of kilojoule. Now, a lot of times we don't talk in kilojoule when we talk about energy. We talk about watts or megawatts or terawatts, which actually what we've done here. For the 3 layers, we have modeled this, and we now have a very nice grid showing you how much heat is there available. So in Niederreuden, we have a bit more than 5,000 terawatt hours. Vaart, there's almost 9,000, and Pechelbron is almost 5,000 terawatt hours, leading up together to, well, almost 19,000 terawatt hours. Now, it's a lot more than Germany uses in 1 year. But of course, we can't extract all of that. And there are calculations for this, and we're going into one right in a moment. The most positive way, you could say that about 2% of that is actually something that you could extract. And then, of course, only in the area that you're actually producing. So unfortunately, we're not getting all of this. Now, what have we added? So this is something that is more or less already known in the old insights, but the presentation is called New Insights, or More Insights through 3D Modeling. So let me add you a little bit more that has been added. And this is the work that my colleague Matthijs Vree has been doing, which is looking deeper into the crystalline basement, which has a very high potential, but of course it's a lot deeper because the crystalline basement is what I mentioned, this deeper part that I did not model. Only the problem always is when you want to model this and something is very deep, not many wells will go there because, yeah, it's deep and drilling is expensive. So at the moment, there are not very great models about it, or there are some models about it, but not that highly detailed. And he worked on it a lot more using gravity and magnetic data to provide additional constraints and have a much better view of what is actually available, or what type of rock is where in the subsurface. So he did this, and then he also recalculated this into a model. And here you can see his results. It's a bit larger area where you can see the top depth, which is ranging here from actually really close to the surface, already more than 1,000 kilometers, to at some places deeper than 5 kilometers here, especially in Heidelberg. We know it's really deep as well. Then he used the top temperature, measured it of these areas, and then he calculated from this top until all the way down to 6 kilometers what is the available heat in place, which is, as you can see here, also really a lot of terawatt hours. Now, what he pushed a little bit further, as I mentioned, you can calculate how much heat can you extract. And in a very positive case, if you look at different literatures, that would be about 2%. So certainly a lot less is available. Now, if you include faults, because they give you additional constraints and but also additional opportunities for extraction, because near a fault you would expect fractures, and fluid can flow through faults and through those fractures. So extraction of heat is then easier because, yeah, you get from one well to the other well. You have a nice, it can form a nice long path. So if you include the faults, this number goes actually up again. So as you can see here, and if you include faults in different lithology, you can see here it's now a lot darker here and a lot lighter and darker here, which is, as I mentioned before, because of the different lithologies that he has extracted from the magnetic and from the magnetic data and from the gravity data. You see that there's a lot more opportunities available. So these are new insights that are being published at this moment, or are under publishing in the next few months or weeks or years. I'm not sure, but I'm sure we can tell you that later. Now, I also mentioned something about uncertainty and risk. And the problem is always with any project is that you want a project to at least make you give you that you will not lose money on a project. And there's a lot of uncertainties you have there. Some of them we can't constrain here. For instance, we can't constrain if some local politician at a certain moment decides that he wants to have more or less energy. But what we can constrain are the geological risks and the exploration risk. And with a conversation I had yesterday actually about it, about how would we actually define it, is that exploration risk is the risk of not successfully achieving minimum levels of temperature, water production, and reservoir temperature. Or in other words, to go from this one well to the other well, the injection and the producer well, you need to have a nice flow path. Because if your water doesn't flow, it's really hard to get it out. And the reservoir temperature needs to be high enough as well. Because if it's not high enough, then you're not getting as much energy out of it as you wish. So what we are looking for is risk reduction. And this is something that we are looking now into a moment as well. So what we want to do is through exploration, we want to reduce the risk. So the quality of exploration work prior to test drilling phase, which is some call it phase 3, in other models it's phase 2, is critical for reducing these two risks of the thermal water production and the reservoir temperatures. It involves a lot of geological, geochemical, and geophysical techniques, which are at the moment used really a lot in the oil industry. Unfortunately, oil has a lot more money than geothermal energy at the moment has. So these are kind of like, so they can take a lot more time to do all these things. However, they are really important. So this is what we're going to look at this moment. So what we want to do is to use the techniques to minimize these uncertainties which are associated with the risk, and then to estimate the uncertainties around the temperature, depth, productivity, and the sustainability of a geothermal resource. Because if you want to have a geothermal resource and you want to produce it, it needs to produce for a certain time. You don't want it to produce for just 5 weeks, because then you have spent a lot of money and you're not getting a lot of energy out of it. You want to use it for decades. 30, 40, 50 years is our target levels that you are looking at. So why are they useful? As I mentioned, well, this is where we are. We want to reduce this risk as early as possible. And the reason is that if we reduce the risk early, we can decide early if a project is worth it or not to work on. And the earlier you see how much risk you have and how much uncertainties you have, the better, the less money you have spent on it. And you can also decide to spend less money based on that risk. So here is a nice graph that I got from our colleague on our project. And this basically what we want to do is this is the normal flow path, which is the longer you work on it, you do some studies, the risk reduces, and the risk, how much risk there is a lot by the time you have the well, because then you have drilled, and you know how much, and you know actually if there's actually something producing. And but of course, the drilling stage is also the most expensive one. So if we can reduce the risk in this level at this moment, before we've spent a lot of money here, that means that we can then have, can keep the money for ourselves. So instead of following this path, which is the not preferred path, where we are staying along in the risk area, we want to stay short in this very risky area with a lot of costs, and we want to go to the place where we have the highest chance of getting actually a lot of rewards. So to do this, we are using a technique called uncertainty modeling. And for this, we're using a stochastic approach, which is relatively simple. You start with a base model. I've already shown you that base model, so we don't have to talk about it. And then we are going to look at uncertainty parameters. So these uncertainty parameters here, as you can see, are basically that the moment we drill, we have a very good idea where our well is, but it might also be a meter or 2 meters or 5 meters off. And of course, because we don't actually see the well, we just have a very good idea. Also, when we measure something, any measurement device has an error, and also the relation between if we measure something at well A and well B at the same depth, if your porosity or your permeability or rock properties will not be exactly the same. So this relationship also has some uncertainties. All these uncertainties we recalculate, and then we do a lot of models with everything, with all the values or with a lot of values within these uncertainty ranges. And if you see here a normal distribution, which is what we often see in a lot of cases, is that the case that we measure then usually is in the middle or somewhere close to the middle. Yeah, the further you get away is a more fringe case, but it is equally valid. So we do a lot of models with slightly different values, all within this uncertainty range, and the chance that it actually hits that uncertainty. And then we combine these results to a model and we create maps. We've done that. And I have an example here of the three layers that I've created, which are the Niederröder, the Vaartfontein, and the Pesselbron. And here you see the mean value that got out of it, which is really close to the base case, but always slightly different. And you see the standard deviation of it. The standard deviation is actually 15%. It's around 15%. It's not exactly 15%, but you get close to that value. And that means that, yeah, if you would start drilling somewhere, you could actually be 15% less of your production. Could also be that, or of your heat in place, and maybe then therefore also your production. Or it could also be 15% more. But for that, you need to do a lot more models. You need to look at different cases as well. P50 and P90 cases for those who are a little bit more into this topic. Yeah, we have a lot of different uncertainties there. Main message in this part is that these uncertainties can help you then decide if you need to know additional constraints the moment you create you want to start a geothermal project. If you want to have more knowledge, or that you actually say like, okay, well, 15%, we would still make money. So let's start it. The project would still be a success. I've not been the only one who have been doing that. My colleague Matthijs has done it as well. And as you can see here, there's a standard deviation. He also created a standard deviation on terawatt hours, which you can see here, where the standard deviation is a lot less near the border of the Upper Rhine Graben, but in the center, and especially here where the layers are really thick, because as you may remember, it was here close to just 1 kilometer, and to calculate all the way to 6 kilometers depth with 5 kilometers differences, there's a lot of uncertainty. You create them as well because you have a lot of volume. So these numbers change them in the area. And with this, this might actually be then a nice area because, hey, this is relatively uncertain, relatively certain compared to, for instance, this area. Now, you remember this map, or you may remember this map. This was the heat in place. And I did a quick idea about, okay, does actually somebody want my heat? Because I'm producing heat and I'm producing electricity, but somebody needs to want it. And here I have it. So here's my map. So is there actually somebody in the neighborhood that wants it? Well, we have here Darmstadt and Worms located. But what we did was we looked at the map and see how much heat is being extracted in a certain area. Here I have that map. It's a little bit of an ugly map, but as you can see here, there are a lot of villages and cities, especially here. Darmstadt and Worms are here. So these are pretty large cities that could use all this electricity. Now here, we're a little bit cold here, so maybe this is not the best spot. But here in Worms, oh, there's actually quite a lot of potential heat. So yeah, maybe it's time to actually look into that a little bit more. Now, I've only modeled this part, but the Upper Rhine Graben is a little bit larger, as you can see here. So there's a lot of area to be explored here and to get more constraints, and that's something that we are doing here in the future. For instance, here is the Mannheim area, and we really want to know, yeah, is this area, is this heat, or is this potential actually also available there? But that remains for the future, which you can see in, which I will hopefully be able to present to you in about a year. So with that, I'm coming to a little bit to a conclusion, because I've been talking about a lot about geological models and how can this help you. Well, so where would you go from here? Say I would start, I want to basically like, hey, this geothermal energy is a really nice idea. Where would this stem from here? Well, first, let's go over what we have been doing so far. I mean, as I've shown you, there are a lot of opportunities in the Northern Upper Rhine Graben for the extraction of the geothermal heat. And it's both for heating and for electricity generation. The models like DGE-ROLLOUT, which will be published within next year, but also the models before, give you an excellent start for further investigation. You have seen now already, like, okay, here's a city and there's actually a lot of potential. I might want to look into it further. But also keep in mind that the uncertainty models that we've produced now, based on publicly available information, will help reduce that risk for you. Which means that, hey, if an area is really uncertain and another area that might have a similar interest and if has less risk, then you might want to go there for your geothermal projects. Now, also uncertainties are always important, because if you're at a certain moment you want to go to the bank because you need money for your geothermal project, it's probably one of the first things they will ask, like, hey, how large is the chance that we will get our money back? With that, we're coming to the conclusion. I would like to thank you all. And I would like to thank especially my colleague Matthijs Vrij for his input, and of course, my colleague Costa.